I've had a request for a problem like number 60 on page 808. So this is an exponential applications problem. And here's our situation. The population, well, I'm not going to read the whole problem because that would just take too long. But please note that I'm doing number 61 from page 809 in your textbook if you want to take a look at that and kind of follow along. So our first task is to determine the constant k to 3 decimal places. And we're using this exponential, a general exponential function. So P of t is the population at any time t. So the population after 3 hours or 5 hours or 6.2 hours, whatever that population is. So that's the population after a given amount of time. Is equal to P sub 0, an initial population, a beginning or a start time population. E is our Euler number. K is our growth or our decay constant. If K is positive, then our population is growing. If K is negative, then it's decaying or declining. And then T is time. So in part A, if we're looking for K, hopefully we can plug in values for all of these other things. So let's look at what we know. Well, we know that we have 60,000 after 7 hours and 80,000 after 12 hours. Okay, we know that, all in all, we've looked at this for 72 hours. But let's think of how we could use this information to find K. So we know, I know 60,000 isn't our beginning, but if we kind of look at it as that's the beginning of what we know, let's let P sub 0 be 60,000. Okay. Then we know a population later, I'm going to hold off on that for a second, is 80,000. Well, how much later? At 7 hours we were at 60,000. At 12 hours we were at 80,000. So 5 hours later we're at 80,000. So we're letting T be equal to 5 because 5 hours have passed during this amount of time. So we've got a population after a given amount of time, a beginning population. Now I know it's not the very beginning of the culture sample, but it's one part and then another part. And then we have 5 hours have passed in that amount of time. So we set this up, we say 80,000, the population after a given amount of time, is equal to 60,000 times E to the K, that's what we're looking for, T, which is 5. So I'm going to rewrite that as 80,000 is equal to 60,000 times E to the 5K power. What we have is an exponential equation, which we just talked about in chapter 3. And so how do we solve exponential equations? Well, we want to isolate that exponential piece. So I'm going to divide by 60,000 on both sides. And when I simplify that, I get 4/3 is equal to E to the 5K. Now that I've isolated my exponential piece, I'm going to take a logarithm of both sides. We like the natural log, especially when we have an E going on. And that result is that the natural log of 4/3 is equal to 5K. Remember, we have a property that says if the base of the logarithm and base of the argument match up, then the result is just going to be that exponent. We'll divide by 5, and K is equal to the natural log of 4/3 divided by 5. That's the exact form. We are asked to round that to 3 decimal places, 0.058 to 3 decimal places. And we can use this growth constant in the rest of our problem because this population is growing at this rate over the entire time of the 72-hour observation. So for part B, now we want to find the initial population, as in the true beginning population. So we come back here, we come to our original skeleton equation, you might say. And we could use either of these two situations that we know. I'm just going to use the 60,000 after 7 hours. So this time I'm solving for P sub 0. I should be able to plug in for everything except p sub 0. So I'm going to let my population after a given amount of time be 60,000. That should be equal to my initial population times e to the k, which I now know to be 0.058, times t. That 60,000 happened 7 hours after the initial population. So I'm going to use 7. So we will solve this equation for p sub 0. P sub 0 should be equal to 60,000 divided by e to the 0.058 times 7. And our instructions say to round to the nearest thousand, so we see here on the calculator 40,000. Remember that you can not only see the display here, but you can also see the exact keystrokes that I used to input that. So if you want to pause the video and jot that down or take a look at it, please feel free to do that. So to the nearest thousand, that is 40,000. So the original population in this culture was 40,000 bacteria. Sorry, when I get to the bottom of my tablet, it gets really messy. All right, part C says, determine the time required for the population to reach 300,000 and round to the nearest hour. All right, so we're looking for time. That means we should be able to plug in for everything except t. Well, I'm going to stick with my 60,000 after 7 hours. I could certainly use the 80,000 after 12. That would be fine too. But I know after 7 hours, the population is 60,000. I know my initial population was 40,000 times e to the k was 0.058 and then t. So I'm now solving this equation for t. I will divide by my 40,000 on both sides. We have 3/2 is equal to e to the 0.058 t. I'll take a natural log of both sides, and we have the natural log of 3/2 is equal to 0.058 t, and then we'll divide on both sides by 0.058, and t is equal to, and you can see that on the calculator there, so it's about 7 hours. So to the nearest hour, t would be equal to 7. So it would take about 7 hours for this population to reach 300,000.